great to be here again. Good to be at the CCC as every year.
First time for me.
First time for you. Then an extra warm welcome to the fabulous Chris Padgett. I'm Carsten, and thank you. We want to discuss with you today the security of the most widely deployed security system in the world. That would be your cell phone. The GSM Association claims 4 billion users. That would be the majority of the world's population is using this technology. Many of those users, including many of you, rely on it every day for the privacy of phone conversations, text message, banking, and so forth. We think this security standard is too old to still be secure, and want to publicly demonstrate that one more time to give this the final nail in the coffin. The quick overview and also the motivation why we are doing this is that the perception of how secure this technology is seems to divert tremendously from the actual security. This is a very old technology. It has been in use for some 20 years, and nobody who knows computers would believe that a system that has never been upgraded in 20 years can still be secure. Yet this is being marketed as high security technology and being pushed into more and more applications, such as banking, where high levels of security are recommended. So we want to clarify this false perception of GSM security and show how weak it really is. As I said, this targets a lot of systems in most countries in the world, and we are not particularly happy about having so many potential victims of this attack. And we wouldn't be doing this research if it wasn't for these vulnerabilities already being exploited. We're certainly not the first to be able to decrypt GSM conversations, and the primary goal of all this research is to inform about this already going on. We do go the extra step of showing a public proof of concept, though, later on in this conference, to make very clear that this is possible to be cracked with very little equipment, so that there's really no hiding place for GSM anymore. Mostly, as I said, to inform about this already going on. Again, we are not at all the first to publicly declare GSM to be weak, too weak for its purpose. There's a long history of academics breaking the encryption function of GSM by the name of A51. It's almost like a game among academics to break it in your way after others have broken it in many other ways. However, all these attacks fall into one of two categories. They're either not applicable to GSM, they break its encryption function, but not as it is used in GSM, or they were never released. The tools were never released, or the data needed for the attacks was not released. So we want to add one more step in this long history of breaking A51 by actually releasing an attack tool that everybody can try at home, and as the last resort for somebody who really badly wants to inform about this being happening all the time. So, because while academics have tried to show that this is breakable for many years, industry is able to break A51, and fairly efficiently so. The machine on the bottom here sells for some $200,000 by manufacturer in India. It is an out-of-the-box GSM decryptor. So clearly all the highly valuable data that goes over GSM is already being intercepted, given that such machines can readily be purchased. Again, we just want to move this information into the open domain so everybody can try this at home. Other than just decrypt solutions, there's a whole bunch of equipment that you can buy on the open market to break different aspects of GSM. Decryption is just one of two main pillars of how you can circumvent these technologies. There are much cheaper attacks that are more active, that would interfere with the handset much more, but that are also much easier to set up. And before I make the point how easy it is to decrypt A51, given some tools we have written, I want to hand over to Chris, who will demonstrate how much easier yet it is, given readily available equipment, to listen in on people's cell phone conversations already.
So, as Carsten mentioned, there's two major families of attacks against GSM. There's active intercepts, where the equipment that we're running is an active base station. It's actively transmitting, it's encouraging phones to camp to it. We are actually broadcasting data to the phones. We have effectively our own cellular network. So I'm going to talk a little about these active attacks and then hand back to Carsten in a few minutes to talk a little more about some of the passive attacks and the crypto that's involved and some of the cryptographic results against the A5 functions. So essentially the way that GSM handsets find the network, there is a special beacon channel in GSM that the base stations advertise themselves on. So when the phone turns on, it listens to this beacon channel and looks for a network that its SIM card is authorized to connect to. When it finds one of these networks, it sends its IMSI. The IMSI is the International Mobile Subscriber Identity. You can think of it kind of like the GSM equivalent of a username. It's kind of a secret, kind of not. GSM supposedly replaces the IMSI with a TIMSI, a temporary mobile subscriber identifier, the moment that the handset has actually connected to the base station. So the theory behind that is that the IMSI is classified as kind of secret, so it's replaced by this completely non-secret TIMSI, which is then used in place of the IMSI from that point on. Now, the trouble with this scheme is that it's all based around two very simple numbers, the mobile country code and the mobile network code. The MCC is a 3-digit number, identifies the country that the network is claiming to be in. So 262 means Germany, the US uses 310 to 316. The MCCs are public. You can look them up on Wikipedia. Likewise, the MNC. Each operator within a country will have its own mobile network code. T-Mobile USA has a different mobile network code within the US MCC than it does within the German MCC. So these can be effectively regarded as a tuple. The beginning of the IMSI will actually be the mobile country code and mobile network code that the SIM was originally allocated on. So you can figure out from the SIM itself what network it's expecting to connect to, and then you can literally just claim that MNC and MCC. When your base station boots up, if you're advertising an MNC MCC of 26201, all the handsets in the area will say, hey, you're T-Mobile, I'm T-Mobile, you can handle my traffic. And they'll just camp to your base station and start sending you their traffic. It's that simple. The only real restriction on it is, well, the only technical restriction, this is completely aside from legal restrictions, obviously. The only technical restriction is that you have to be the strongest signal. If the phone sees multiple T-Mobile MNC MCCs being advertised, it will just camp to whichever gives it the strongest signal. It's not difficult. So as long as you've got a reasonably powerful signal, you'll get all of the handsets in the area sending you all of their traffic. This technique is called IMSI catching. It's so named because you do get the IMSI rather than the TIMSI. You can detect it from the phone. The phone has the capability to tell the user space or any other part of the phone what MNC, MCC it's connecting to, whether or not it's got crypto, all of this stuff. The vast majority of baseband implementations that we've looked at simply don't care. They'll quite happily connect to pretty much any base station we throw up. So you can actually build an IMSI catcher from open source components. This is essentially the hardware basis for it. This is the Universal Software Radio Peripheral, the USRP. It's a very common piece of hardware. The only modification that we had to do to this, you can see there's an extra little board here. The USRP has a 64 megahertz clock on board, which is not stable enough for GSM. So when you're talking about GSM 900, when you set your frequency, you have to set that to an accuracy of less than 500 hertz. So this extra clock gives it an accuracy of less than half a part per million. Very good frequency stability, and that's basically it in terms of the hardware. Very, very common to see these, and the clock modules are relatively easy to obtain. In this particular case, the clock module doesn't run at 64 megahertz. All of the GSM clocking is derived from a 13 megahertz clock, so this is actually a 52 megahertz clock, so that we get multiples of our primary frequency, and we don't need to do frequency translation in software. So the hardware is very simple. The software side, OpenBTS, is effectively a software implementation of the air interface for GSM. The combination of OpenBTS providing the interface and Asterisk providing backhaul connectivity, it's relatively easy to set up. Asterisk can be kind of a bear to configure, and OpenBTS can be a little picky about library versions, but as long as you can work a configure script and a make file, you can build your own IMSI catcher. It's not tremendously difficult. So once you've built this, how do you actually operate it as an IMSI catcher? Well, if you wanted to break the law, you just pick an MNC tuple for the network that you want to spoof, and just configure it. Find an open channel, find a channel that nobody's currently transmitting on so that you're not overwriting anyone else's signal, you get a nice clean signal, and just run the base station. Wireshark is great for monitoring what's going on. Wireshark has two analyzers in it. One which does SIP traffic, so when the calls come out of Asterisk going to your backhaul SIP provider, Wireshark has built-in capabilities to just decode the SIP traffic, decode the GSM codec within that audio stream, and just play it back or save it. Likewise, if you can actually get access to the raw GSM packets, it does also have a GSM analyzer as well. The alternative is you can capture the data straight over the air with AirProbe. That's another open source package, again uses the USRP. So there's plenty of open source software around for building IMSI catchers, for running test base stations, for sniffing traffic off the air, depending on what attack you want to implement. So obviously we have the equipment, we've played with this a little bit. Obviously we haven't spoofed any real networks, honestly. However, we have found a few interesting bugs in baseband implementations. One particular example was an iPhone 3G that we came across. We don't know quite what was wrong with this iPhone, but we set our MNC MCC tuple to 00101. So it's a test network in a test country. No phone should ever connect to that. And the iPhone's still connected. So we thought, okay, the phone's going to camp to whichever base station has the strongest signal. So we unplugged the transmit antenna, and the iPhone's still connected. So in software, we disabled or turned the power amplifier on the USRP down as far as we possibly could, put out the minimum transmit power we possibly could. The iPhone still came back. Then we thought, well, GSM 900, which is used in Europe, US uses GSM 850. And the great thing about that is that the 902 to 928 megahertz band in the US, it's called an ISM band, Industrial Scientific Medical. It's not quite a free-for-all, but it's about as close as you're going to get. And it overlaps this GSM 900 band. So we thought, okay, let's set up our BTS on a channel that doesn't even get used for GSM in this country. It's an ISM band. The phone should not be doing anything in the ISM band. The iPhone's still connected.
And this wasn't even our iPhone. This was some random iPhone in the neighborhood. We had no control over it whatsoever.
Yeah. The particularly amusing thing about this is that on several occasions we've actually tried to deliberately get iPhones to camp to our BTS, and the vast majority of iPhones that we've tested won't go anywhere near this thing. They can't talk to it. So this one particular iPhone 3G was, I don't know what was going on with it, but it certainly just, it was like it was banging its head against us saying, hack me, hack me, hack me, hack me. Absolute craziness. Some other bugs that we found when we've been playing around with IMSI catchers and base stations. There was a post on the OpenBTS Discuss mailing list. A student in China sent a message saying, "I think they're going to kill me." He'd set up OpenBTS as an IMSI catcher in his classroom, and all of his classmates' phones had connected to it. And obviously, the network name that came up on the phone was OpenBTS. He'd left it as the default. That kind of clued people into the fact that something was going on, and they got a little upset with this, and so he shut down the base station, and the OpenBTS network short name remained, even after they'd unplugged the batteries, hard rebooted the phones. As far as I know, they still say OpenBTS on them. It's... and again, the great thing about it was that all of the cheap and cheerful, like candy bar phones, they were all absolutely fine. They just quite happily said, you know, China Telecom when the BTS was removed. It was all of the big expensive smartphones that cached the network name and wouldn't get rid of it. Another good one, OpenBTS has there's lots of layers of registration in GSM. There's the HLR, the hardware location registry. This is what is responsible for actually authenticating the phone into the network. That's generally handled by Asterisk when you're dealing with OpenBTS. But OpenBTS does also have an air level authentication. So you can authorize specific IMSIs to even camp to the base station regardless of connecting to any back-end connectivity. The bug with OpenBTS was that it was supposed to reject handsets. If you had open registration disabled, it's supposed to reject handsets by saying you're not authorized. Instead, it sent the "you've been stolen, please disable yourself" message. In the case of iPhones, this required a hard reboot to fix. I don't know how many people here have ever tried removing the battery from an iPhone. In other cases, the phones were actually disabling themselves permanently. So this was just a random thing that they just happened to put the wrong message in at the wrong place and just kind of stumbled across this. And it's a really effective denial of service attack. So the conclusion that we're coming to with all of this is that nobody is looking at this. If these kinds of bugs existed on the internet, they'd have been exploited years ago and they'd have been patched years ago. But for whatever reasons, GSM has not been looked at. So all of these baseband implementations have incredible bugs in them. We believe that you know, there's exploitable baseband bugs in pretty much every GSM stack in every GSM phone. They tend to be functionally tested rather than destructively tested. So they're tested to make sure that they actually speak the GSM protocol correctly, but they're not tested to see what happens when the BTS doesn't speak the GSM protocol correctly. So obviously this isn't too great for security, and we're coming across an awful lot of really, really big juicy bugs in some really big juicy cell phones, just purely by getting it wrong with OpenBTS every now and again. So that's the active attacks, and Carsten's going to talk a little about the crypto passive attacks now.
Yeah, before going into that though, let me skip back a couple slides and stress one point on this slide that gives a strong insight into the security level of GSM or their security philosophy. An IMSI catcher is extremely easy to set up and cheap as well. $1,500 is all you need in equipment. The only thing easier to set up an IMSI catcher in GSM would be to detect that you are on an IMSI catcher. There are very strong cues, changing lag, that's the location area code, silent messages being sent to you, a whole long list. If anybody is interested, I can share that with you. None of the phone manufacturers seem to care though. Not a single phone would have a tool that tells you when you're under attack, even though it would be so extremely simple to detect. In fact, it's getting worse.
There's also not a single phone that we've seen that if we connect it to an IMSI catcher and negotiate plain text connectivity, there's not a single phone that we've encountered that will actually alert you to the fact that you're on a plain text network with no crypto.
Right, so that's one of the cues, and that's actually the point that I wanted to stress too. That is one of the cues, the lack of encryption that everybody should be able to detect. The GSM standard says that a cell phone must show a padlock when there's encryption, or at least show an open padlock when there's no encryption. Most phones do that because the GSM standard also says that the SIM card, your network operator, the SIM card, can deactivate this feature. And most every network operator chooses to hide the fact from you whether or not you're under attack. It's a single bit on the SIM card that I could simply set, and we have seen random SIM cards that have this, that would allow you to see whether you're under attack or not. But most everybody chooses not to. So there's a whole conspiracy here, but among the network operator and the handset manufacturer and pretty much everybody involved trying to hide from you when you're under attack, which I think sets the baseline security pretty low to begin with. So everything, all the advanced crypto attacks we're going to talk about now are to be seen in this context of an already low security level. But yeah, let's get into the fun stuff. Cracking what the GSM Association up until this summer claimed as their #1 security feature. They don't anymore. I'll get to that in a little bit. Their encryption function, A51, a 20-year-old encryption function. It uses a small enough key, which makes it vulnerable to pre-computation attack. The attack generally works something like this. You have the equivalent of a phone book. A data set with 2 columns. One column in this case being the data you observe over the air, the other column being the secret key that was used to generate that packet you see over the air. If you have a complete phone book, you can take any data from that you observed on the air and look up in this phone book the secret key that was used in generating it. Even though A51 uses a small key, it's not small enough to actually compute this phone book and store it in its entirety. It's a couple petabyte, and if you were to straightforward just crunch through all the keys, you'd need tens of thousands of years, pretty much. Still, there's optimizations. Philip Oechslin, who was speaking here before, contributed a couple of ideas, and there's a whole research stream piling up ideas on how to do pre-computation attacks better, the so-called time memory trade-offs. And now, for the next couple of slides, I'll mostly speak about two things: how to compute this codebook much faster, and how to store it much smaller to make this attack actually practical. We have done almost no of the computation work ourselves. Let me give that as a disclaimer, but this was a complete community effort. Some of you might have seen our talk at the HAR conference, our ad hoc talk. Nobody had told me that I was supposed to give the talk, and I was trying for days to find a person that did similar research to me. So yeah, we had an ad hoc talk at the HAR conference where we kicked off this research, and since dozens of people have helped us compute these tables. And here's our approach, how we got these tables to be fast to compute and small to store. Of course, first we need to port A51 to highly optimized hardware. Since we wanted to keep it as cheap as possible, our primary targets were graphic cards. CUDA from NVIDIA and Brook from ATI graphics cards. Turns out they're much, much faster, or at least more energy efficient than CPUs. We then had to find a way of storing all that data smaller, and we used an approach called the rainbow tables, something Philip mentioned before. And finally, we needed volunteers to crunch through all these computations and compute the tables, some of which have already shown up on the local FTP network, and we hope to see more. I bet a couple of you brought stacks of them. So let me walk you through the different steps. First of all, we needed to optimize A51, which we saw was a trivial task since it's a crypto function, and people are generally good about optimizing crypto functions for brute forces, so they can try all keys as fast as possible. Which was pretty much our baseline, the fastest A51 we could find. We ported it to CUDA at first, the NVIDIA graphic card standard, to have it as parallelized as possible. We find something on the order of 400 CUDA cores on a single graphic card, meaning we can crunch through 400 computations at once, where on an Intel architecture, despite pipelining and everything, we had at most squeezed in a few dozens. FPGAs are even more optimal, but we didn't at first have much access to FPGAs, and we're lacking FPGA programmers in the later stages of this. I'll get back to FPGAs and on one of the later slides. We still need help with FPGAs, but now in a different part of this project. So once we had everything parallel, we wanted to create every single engine as fast as possible. And it turns out that in A51 you can compute 4 bits at a time, so you get a 4-bit speed up there, which we sort of finally created the highest performance A51 one could dream of, until we encountered bit slicing. Great technique. If you need to brute force anything, use bit slicing. The idea being that you apply the same operations on very many data streams at once. Something that comes from multimedia was introduced to Intel through MMX, and now in the SSE, the CUDAs of course do it too, since they compute large, vast quantities of data. So through bit slicing again, we had a factor 4 speed up, and I think we're pretty much at the max of our hardware now. We initially thought we needed 6 months on something like 100 computers with graphic cards. We got that down to 3 months on 40 computers, and I think we computed all these tables that we set out to compute. We certainly have enough to decrypt A51 calls with a very high probability if the call is long enough, but we want to make it as efficient as possible, of course. So at the end of this conference, we'll know for sure, and there will be a workshop where we test this. So for the next couple of days, we asked you who brought tables to, well, please first sort them to store them more efficiently. The tools have just been posted to the website, and then upload them to the local FTP servers. I've already seen a couple, so people have started uploading to the FTP servers, including torrent files. Thank you very much. That is very helpful, so that people that take them home can keep sharing them. But we'd like more tables, so send as many tables through the local FTP servers and mirror them as much as possible up until Tuesday evening. We'll then collect them all and do do a public demo on Wednesday. We decided not to do that on stage since we'd have to rush through and everything, but we'll explain the tools in detail. And if you already have GSM data or want to artificially generate some to challenge us to see whether we can decrypt it, please bring those to the workshop. They'll be a fun exercise. So yeah, we are done with the table computation. From all we know, we're just facing the one last logistical hurdle of bringing terabytes of data together in one place. The cracker, by the way, we found that the most efficient way of cracking this is by distributing the tables across USB sticks. So you'll see a computer with some 16 to 32, depending on how many tables we find, USB sticks hanging off of it, which is the most cost-efficient way of doing it, it appears.
We actually considered a lot of different architectures for the cracker and figured that by far the biggest problem is the latency of the drive, which is why flash memory is good. It's got very low throughput, and obviously we're cascading kind of USB keys and USB hubs off of each other. So the latency is pretty good because it's USB, it's flash. The bandwidth sucks, and we don't care. It works very well.
Yeah. That turns out to be the biggest bottleneck, but given cheap USB sticks, even that doesn't increase the cost of the cracker very much anymore. Unless there's any questions right now about the general approach, motivation, all of that, I'd go a little deeper into the technology and how rainbow tables work for now. Is that all right? Any questions so far? Okay, so rainbow tables. Now starting from the idea of a code book with just two columns, the key and the output. We want to store this more efficiently, and the way we do it is have a code book with more than two columns. Starting at a random value, that could be a secret key. We apply the A51 function, marked K in this picture, to derive what we then use as the key into the next A51 function, and so on and so on. And we apply A51 up to 1,000,000 times to then derive our end value. And we'll only store the last and the first value of this chain. We do this for many chains, and we'll only store the yellow and the green in this picture. Now, if we want to, after the fact, after computing a very large such table, crack something we observe on the air, say the B951, we see that on the air, want to know what secret key was used. We apply A51 to this number, arrive at something that we can't find in the yellow, so we have one lookup that goes into nowhere. We apply it again. Now we have something that we'll find in our yellow table on our hard disk or USB stick, and we know that with some high probability, the key we're looking for is in this chain. So we start at the beginning and compute until we hit the value we see in the table, we saw in the air, and the value just before that is a secret key. Does it make sense? So if this has sufficient coverage, if this table is really large, then we should be able to decrypt pretty much any conversation with this. Now there's two drawbacks to this that kind of limit the size of these tables, both of which have found tweaked through academic research and through this long history of papers. And I want to introduce both ideas. The first idea gets around the problem of having to go to the hard disk too often. As we pointed out, the hard disk seems to be the bottleneck. And if you have a chain of length 1,000,000, you'll have to go to the hard disk 1,000,000 times just to find whether or not the value you're looking for is actually stored in your yellow column. Now the way to get around this is called distinguished points. In distinguished points, you only ever store values in the last table that fulfill a certain criteria. In this case, the criteria being the last half of the value is all zeros. So you apply the A51 over and over and over again until you hit a value that fulfills exactly this criteria, and that then is the end of your chain. Of course, the chains are of different lengths, since you can't really predict when you will hit such a value, but all of which end in the same type of number. Now again, if you observe a value on the air, you apply A51 to it over and over until you hit such a value, and only then you go to the hard disk once and see whether you stored the value. So you dramatically decrease the number of hard disk accesses needed. Good so far? So this is a great optimization, and I'm very glad that somebody else came up with this before, because this is just ingenious. It still has one drawback, though, that it shares with the plain tables, and that is a fairly high number of collisions, or fairly high impact of collisions. Collisions being if you ever encounter the same value twice in your table, the remainder of your chain will look exactly the same, and they'll end in the same value, right, in the same distinguished points, since everything is deterministic from there on out. If you do have too many mergers, adding more and more lines to this table doesn't increase the coverage. So you're creating more and more redundancy without actually getting closer to breaking calls. Now, what you would do then usually is start a new table. And again, if that fills, that doesn't produce more entropy anymore, you'll create a new table and so forth, and every new table increases your attack time. So you're very inefficient. Academics have also come up with a great idea to get around that problem, and that now is called the rainbow table, where in every step of this computation you apply a slightly different functions. These are all still type of A51 function, probably just with a different constant XORed into the function. And since they're all different functions, kind of different colors of a rainbow, this is called the rainbow table. If you do have a collision now in a rainbow table, unless the collision happens in exactly the same column, the chains don't merge, since the next computation is going to be different. So that gets you around the problem of mergers through collisions, which allows you to compute much larger tables, get a higher coverage with a smaller number of tables. We tried both approaches. Both have their advantages, and I think we tried. We're the first to apply both at the same time, which is one of the optimizations we pulled to make this much more practical than previous A51 attacks. So we are computing 32 distinguished points, and after each of the distinguished points, change the color of the rainbow. So here's a rainbow with 32 different round functions, each round function ending in a distinguished point. And we only store, again, the last and the first column. Okay, enough with technical deep dive. I think that was plenty, but I wanted to give you at least one nugget to chew on. If there's need to discuss this any further, we do have a mailing list, and questions are much appreciated. Now, the end result of applying all these techniques is that we need to compute a few terabytes of tables, so something very manageable on cheap hard disks, to be able to decrypt calls with a fairly high probability. This probability increases every week, since we find more and more sources of known plain text. The more often you get to look up a call in the tables, the higher the chance that you will find this call's secret key in the table, at least the session key. For those who know A51 and how it's used in GSM, every frame starts with the same key. It's called KC, and then a random number is applied to it. So in theory, every frame should start with its unique key. Turns out that you can roll back the A51 to the KC. So breaking any frame during a conversation allows us to decrypt all frames. That's some background that might need to be said to convince some people that this is actually possible. We'll post the backtracking code in the SVN pretty soon. It's pretty much through testing. Okay, so the the story now is we have computed terabytes of tables, and we can decrypt GSM calls if we do get enough plain text. This is this list of where we know known plain text is. I think this is novel, and I just wanted to throw it out here to have this in the open. So far, every GSM cracking project, at least that I know of, I'm sure industry is a little ahead there, was built upon the assumption that you have one burst, one frame that you would know and that you could crack. Now it turns out that there's a whole list of frames you can collect, and in fact, the longer a call is, the more frames you can collect, not just the first one, which dramatically increases the chance of finding something in even small tables. We have even a few hundred gigabytes of tables should be enough to decrypt a call that's sufficiently long. Yeah, so without going into details, this now should convince everybody who's familiar with GSM that we can gather enough data and that we have the tools to decrypt it. I hope you're convinced too. Now, here's what the GSM Alliance says, and let me paraphrase what the official statement said this summer. They said, pretty much, we think these researchers will be able to decrypt GSM soon, so A51 might not be as strong as some claimed. However, A51 isn't even our main security feature. Channel hopping is, frequency hopping is. So they've moved the target, and well, fortunately they give us some high-level advice on how we should hack them. They say we need a radio and some software. So let's see. Now, one disclaimer. We have not built a GSM interceptor and don't plan to advertise it during this talk, since that would be strictly illegal under many wiretapping laws, but just hypothetically, if you were to build one, these are the components you would take. You'll take a radio and some software, as they have pointed out. The radio being this exact radio, or rather the second version of this exact radio, the USRP. It already can intercept large chunks of the GSM spectrum, and the way that the GSM spectrum is divided among the different operators, usually it can capture a whole operator spectrum. That again is divided into downlink and uplink, so you'll need two of these devices to capture the entire GSM spectrum, which is needed to get around that new high security feature, the frequency hopping. So instead of following the secret hopping sequence, what we do is we just capture all of it and record it until we find the secret key, until we can then derive the hopping sequence, go back to the data, and see which channels we need to decrypt. Now, not all work that is needed on the USRP needed to make this super practical has been done, and this is what I was saying before. So if somebody were to create a project doing this, hypothetically, he would be asking you now if you had any idea on how to program the FPGA on this. We really badly need somebody to help us with that. Not because this is a showstopper, but because currently this device outputs 40 megabytes per second, and there's two of them, and this is just hard to handle for a computer. It goes over Gigabit Ethernet, but the computer that also needs to decode all of that is a little overwhelmed. So to make this super practical, somebody please move some of the components of the software into the radio. The software being OpenBTS, that's also used as the IMSI catcher, that already can decrypt decode all the information we need from GSM. At the moment, it decodes only one channel at a time. They're already planning to up that to several channel support, not for intercepting, just for just to be able to support multiple handsets, or more than they currently support. So this is coming, and all the other features we need in OpenBTS, if somebody were to repurpose this as an interceptor, are coming. So the only work left is really on the USRP side and on getting the data rate to a more manageable level. But yeah, thank you, GSM Alliance, to point us to the fact that the cracker isn't complete yet. I suspect that the community will complete it now that this seems to be the new high security feature. I was going to end with a strong statement that network operators should upgrade to A53, which is the new standard. But over the last weeks, I've become more and more suspicious over A53, and that could break soon too. So the state at the moment is A53 is more or less a mandatory upgrade. At least the GSM Association would like the network operators to upgrade, and has said that for many years. Nobody was, I think, the exception of SFR in France, has a very limited A53 operation, has done so yet. So the network operators are completely ignoring this call. Maybe for the better, since A53 seems to be breaking two at the moment. Two hints towards that general suspicion of mine. This is a slide from a RAM session talk last week at Asia Crypt, where a couple of well-known cryptographers have looked at Kasumi, which is A53, and have derived what I think is a practical attack, what I think is the start towards some research that could lead to a practical attack. The data requirements here are still way too high, but as with most crypto research, others will improve upon this and make it practical to decrypt A53. Even before that is happening, the GSM standard has another weakness that is already overshadowing the A53, A52 realm, where phones sometimes use two ciphers, and you get to choose which one you want to break, A52 being the weaker one. The same attack I'll outline now also applies to A53. Works something like this. You intercept, again, not with hardware that we'd ever have touched, a cell phone call that uses A53. And you observe during the cell phone calls in the beginning where the cryptos agreed upon a random number. After the call is done, you set up a fake base station, an IMSI catcher, and you ask the phone to please initiate a call using the other cipher, the weaker cipher. We can already break A51 or even A52 if you ever find a phone that supports that still. And you send it the same random number. What the phone will do is it will use the same secret key, which then you can break and go back and decrypt the call you've intercepted before. So long story short, as long as A53 coexists with anything that is broken, it too can be broken in the current scheme of deriving the secret keys through the same key derivation function. So it looks to me as if GSM is more thoroughly broken, and an in-place replacement of the cipher won't fix it completely. Yeah. So as I said, I'm actually torn about this whole thing. I would like to see everybody upgrading to A53, but perhaps that's the thing that somebody else will speak about next year and see that broken. So perhaps a more wholesome discussion is needed about the security standard that 4 billion people deserve, and a more open approach to getting there. By the way, all the components needed to pull off this attack are also in the open. These are all open source projects or data distributed through FTP servers here. So this can already be done in the one network in the world that uses A53. Now to try to end on a somewhat positive note, we've built lots of tools. We've tried to keep them as generic as possible, as flexible as possible, mostly to support other projects that might want to do rainbow table attacks as well and need really, really fast implementations. So here's a whole framework that you can use for your project. If you do have an interesting crypto function with a reasonably small key, say everything up to 70 bits, we'll help you speed it up to compute rainbow tables. So please get in touch. Also, if you can program this to for the hypothetical interceptor, we'd much appreciate your help. And with that, I want to thank you very much for your attention, and hopefully we'll get some questions now. Thank you very much.
Any questions?
Can we turn on this microphone?
Check. Hello, check.
Oh, the question is whether were we able to verify the Asia crypt results? And the answer is no. The ePrint paper is going to be published next week, so then we'll be able to. But the answer also is we don't have to. Shamir is on it.
Yeah. There is also the question of the applicability of the A53 result to 3G conversations. Even though Kasumi itself may be cryptographically broken, it's not immediately apparent how to apply that to a 3G system. So there's a lot of work yet to be done there.
Yes, it's a first attack. There will be a research stream, and there will be better attacks. But at the pace at which A53 is being introduced, I suspect it to be dead before it's hitting any networks.
Yeah. Question here?
Yes, so thank you very much, sir. My question is, with data being very easily secured using layers in the OC protocol that are encrypted, is there anything that the end users can do to restore their privacy in voice conversations, instead of just to go all data?
That would generally be our recommendation. So the question is there anything that end users can do to protect themselves in the face of these vulnerabilities? In terms of GSM itself, not really. The only real way to secure a GSM handset is to treat it as an IP network and just tunnel a secure protocol over it. Just treat it like the internet, really.
Yeah, there are phones that do end-to-end encryption. There are several companies selling such phones. Most of which, though, rely on some form of key exchange, either before the call or during the call. Most of which also send data instead of voice. So there really isn't anything to upgrade plain GSM voice, what you get in your monthly budget, to make that secure. Yeah.
Yeah, the encrypting handsets as well, they tend to be extremely expensive. I've seen them sold for $50,000 each.
Oh no, for low four digits we'll buy you one here in Berlin.
Ah, okay. Yes, question here?
Yeah, how about 3G and 4G networks? Do they use the same security or insecurity functions, or are they completely different?
Good question. 2.5G, meaning GPRS, uses also 3 different ciphers. that may or may not be related to A51, A52, A53. Nobody really knows yet, but definitely A53 is in that mix. 3G networks use A53. 4G, I don't know. As soon as Kasumi, the A53, is thoroughly broken, all of these networks are insecure.
I believe 2.6G edge is closer to 3G than it is to GPRS, so I believe it uses A53 as well. I could be wrong on that, though.
Thank you.
Industry tries to sell stuff several times when they invented it once, so there is also GSM-R for railway networks. And I don't know about Tetra, used for public safety, etc. To what extent are your findings applicable to those kinds of networks?
I wouldn't know, but so the question is whether our findings are applicable to GSM-R, which I've never encountered, or to Tetra, police radio. I don't know, but if anybody has a Tetra device that's not needed anymore, I'll be happy to pull out the ROM and look at it.
My expectation would be that there is sufficient code reuse and silicon reuse between the various systems that are all ultimately derived from GSM, that there's going to be enough crossover that some of these attacks or close equivalents will be effective. I would expect.
You said that there should be a lock on your display of your cell phone if the call is encrypted, but this is disabled by the SIM card in your phone. Is there a possibility to activate this on your personal SIM card so that you can see if the call is encrypted or not encrypted?
Yeah, so the question is whether you can bring back the padlock functionality by patching your own SIM card. Not trivially. You can't write to the SIM card unless you have the secret keys to access it. There are, to my knowledge, proxy little sheets that you squeeze in between the SIM card and the phone that would allow you to flip bits. So if you were super paranoid, you might try to squeeze that in. Another thing you can try is get prepaid SIM cards off of eBay. It's a toss-up. Some of them have the bit set, some not. But you'll eventually find one that does, and perhaps bring back some of the information you deserve to have to begin with.
If all else fails, if you do set up an IMSI catcher and you do spoof your local network, as far as the phone is concerned, you are that network. So whatever the security mechanisms are protecting updates from the network to the SIM, it's plausible that you could potentially break that cryptographic signature as well and send your own updates to the SIM. We haven't looked into it in much detail, but it is plausible because you do own the network at that point.
As far as I know, there have been rainbow tables calculated before, but I never understood why were they not published.
Yeah, well, neither do we. The question is why have previous rainbow tables not been released? And well, I can think of three explanations, and I won't say which one I believe most strongly. And I think it could be intimidation. There's a lot of well-funded agencies and companies that are interested in this not being public. It could be the whole responsible disclosure debate. How many years do you give them until you give out attack tools? We thought 15 years was enough. Somebody else might not think that. Or it could simply be commercial interest. If you can sell a unit for $200,000 and you're one more player in this market, there's some real money to be made here.
So were you intimidated by the industry somehow?
Good question. No, but
not yet.
Not yet. Well, we set it out. We set this out as a as a project without a single point of failure from the very beginning. We announced this project the day we put all our tools online. Everybody could have continued from there on. And in fact, we asked everybody to compute these tables, so never to have them in a physical location all at once where they could be taken away, or even just in one jurisdiction where a judge could rule over them. So yeah, we took, in preparing this project, we took a couple of steps to make sure that there's no point in suing us.
Okay, thank you.
Just a brief comment in regard to the previous questions concerning GSMR and Tetra. First, GSMR, at least voice-wise, there's no difference to standard GSM. GSMR has some very neat features like functional addressing, call priority, etc., but as far as these components are concerned, it's essentially identical to GSM, so it's prone to the same issues. Mm-hmm. Second, Tetra, that is a completely different story because, I mean, a plain Tetra network will not give you security that's worth being called by that name, but the various national implementations usually have some end-to-end encryption that is not always switched on, but it can be switched on, and if it is, then that's vastly superior to A5 whatever. Okay, well, thanks for that input. That was news to me. I'd still like to repeat what I said earlier. If anybody has access to Tetra hardware, and I mean this seriously, even if you know that it's just implemented in the silicon chip, we want that hardware and we want to get this cipher out. It's just one more proprietary crypto system that hasn't undergone any public review, and that a lot of high security organizations rely on. We'd love to look at it and perhaps find that somebody has created good proprietary crypto. We haven't found a single example so far.
I wonder if the rainbow tables that are created in the community have to be protected against manipulation, or is that not needed? And if that is not needed, then why?
It's actually really quite trivial to protect against malicious tampering of the rainbow tables. All you have to do is just try and look something up in it. If you look something up in the table and you don't get a correct result, then there's something wrong with the table and you can just discard it. It's very easy to verify correct functionality of them.
Right, so to test a table, you have to test a very small subset and recompute it. And with just a tiny fraction randomly chosen, you will find tables that have a majority of junk in it. So there's no way of denial of servicing just by uploading tables that aren't real. But good question, thank you.
Just one precision on the railway GSM usage. That was introduced because there's some kind of very stringent regulation, so that, for example, you need to call a train and have a connection delay of at most a few milliseconds. So in order to achieve this kind of good performance, they removed some optional part, which is encryption and authentication. So for emergency calls to train, they are not encrypted and not authenticated, and you can look in the UIT or ITU specification, it's documented there. So. Just very nice.
We have also heard hearsay that encryption is required to be optional in GSM handsets, at least in the US, specifically so that law enforcement can turn up outside your house with an IMSI catcher and listen to your cell phone calls.
Oh yeah, one information we didn't give you when we were talking about IMSI catchers. An IMSI catcher is trivially detectable from the network side as well. So the network operator in any given country knows where IMSI catching is happening. Do they care? Do they call the police to tell them that the police is just pulling off an IMSI catcher? Of course they don't. So the network operators choose to not care as well. As I said, everybody in this food chain chooses to leave you as the user as uninformed and as unprotected as they can possibly get away with.
And at the same time, if you ask the network operators about the security of their networks, they will absolutely swear until the day they die that they are secure, that GSM traffic is secure, cannot be intercepted, as good as a landline. In reality, it probably is as good as a landline in the States. Thank you, AT&T.
Yeah. And they don't just publicly try to push this as a security technology, but more hurting to the overall security in new system developments, new payment system, new banking applications. Many of them consider using GSM as a trusted channel between the user and themselves, which is a terrible idea, especially given the option of doing application level encryption, these being data applications. So yeah, there's a lot of nonsense about the security of networks being said by the network operators. And I sometimes wonder if they really believe that themselves to any degree. Another question?
Yes. So if it is detectable, when do you think there will be applications for smartphones that can be installed that will access the available data and then alert the end user of the current phone status?
The biggest problem with that is that it's very difficult to get baseband information out of a cell phone into user land. Generally, cell phones will have at least two processors, one to run Android or whatever operating system is running, and then a completely separate processor to run the baseband. And they'll just communicate over a standard serial link with a standard AT command set. So there are some phones, like some Blackberries, if you can expose the engineering menu on some Blackberries, you can expose some of the baseband information to user land, and you can write an application to parse it. In the majority of phones, though, you have absolutely no insight into what's going on in the baseband, so you'd have to find some kind of backdoor into it, some kind of side channel maybe to try and find information about the call and about the network status. So in theory, it's possible to do on any phone. In practice, I think the only handsets that we're reasonably confident you could do it on is the Blackberries with the engineering menus.
Yeah, so the short answer is we're the wrong people to ask. That the handset manufacturer would have to choose to implement such a tool, or at least to expose the data needed. There won't be an iPhone application detect IMSI catch, since that application doesn't have access to the data yet. There's some iPhone people here, I know. Maybe we can talk to them. Yes.
Can you talk some more about detection and what the baseband would need to be looking for to do that? How it can be detected?
I think the primary thing for it to look for is a lack of crypto. If you're connected to a network that has asked for you to use a plain text connection, that should just be an immediate red flag.
If you have seen the same network use crypto before. Yes, about half of the networks in the world do not use crypto. Half of the networks in the world. Yeah, but there's a long list of red and yellow flags you could look for to detect an IMSI catcher. Anybody who has access to baseband information, I'll be happy to share that list and create an application with you on any phone, really.
There's a lot of signs. OpenBTS isn't perfectly compliant with the GSM spec yet, so you could detect it from the protocol. I mentioned the clock on the USRP is not particularly stable, so the clock that we've added is better. It does bring it into within the tolerances of the GSM specification, but it's still not as good as the clocks that you'll get from actual, legitimate base stations. So there's lots of side channels, lots of direct channels as well for detecting the attack.
We're through with the questions, okay. I take it?
I think we're out of time.
Again, so thank you very much.
Thank you very much.